So we'll pick up where we left off. Okay, we've been talking about galaxies. So of course over here you see galaxies. What this black thing is basically saying you are here, okay, on Earth orbiting our sun. Our sun is a part of the Milky Way galaxy. How are we going to know how far away things are? And things that are relatively close, like objects within our solar system, we can actually use radar, kind of bounce some energy signal off of them and see how long it takes to come back to get a sense for how far away those objects are. We talked about using parallax to gauge distances to stars that are relatively close. Remember the video we watched on this week actually had the guide showing the pole parallax where you have an object close to you, like your finger. You close one eye, you close the other eye, and it appears to change its position. We can use that to see how far away some of these relatively nearby stars are. Then actually this week we talked about using standard candles. So the other stuff kind of is using standard candles. It's kind of small, but you remember we looked at, actually this is an HR diagram right here, and there's two clusters thrown up on that HR diagram. The Pleiades and the Hyades, which are both in the same constellation from our perspective. They're both in Taurus. But the point here is that, remember the Hyades are generally brighter. The whole set is brighter. And the Pleiades are dimmer, so actually we can gauge how far away the Pleiades are from the Hyades. Okay. Then we talked about, remember Edwin Hubble actually used this pulsating star in the Andromeda galaxy. That's a Cepheid variable. Actually, depending, and doesn't go this fast. It was like 50 days, right, the one I looked at. So it takes 50 days to get brighter and then to get dimmer. To do one whole cycle is 50 days. So anyway, he carefully used the Cepheid variable, how its period, to know its luminosity, and then compared its luminosity to how bright it was, and came up with a distance to the Andromeda galaxy. So we can use Cepheid variable as a standard candle in that way. Another type of standard candle we talked about that gets you even farther down the road is if a star blows up in a distant galaxy. So we looked at actually kind of three scenarios, kind of the before and after, and the farther away the galaxy was, the dimmer the supernova appeared to us. Now this is not just any supernova, this is that type 1A. This is that one where a white dwarf has a companion, it's getting dumped on, it gets the 1.4 solar masses and it blows up, okay? So actually you can compare its apparent brightness with what we know its luminosity would be to know how far away it is. And then, I know last we did, excuse me, in lecture we talked about Hubble's law. And remember, that was this where if you have, he took a bunch of galaxies and he basically said, there's an exciting straight line here. He basically said that the distance from us, okay, and then this was recessional velocity. I'm not spelling that right, but you get the idea, velocity. Okay, so basically he said that the farther it is from us, the faster its recessional velocity. Okay, and we can actually use that then. We can gauge its recessional velocity, and we can pick off distance using Hubble's law. So it's all kind of cool. This is just how do we get to distances of objects, distant objects. So just like we kind of introduced clear back at the beginning of the semester, the universe is expanding, okay? Remember the raisin cake? Basically, you are one raisin, and all of the raisins are getting farther from each other as you bake your cake, okay? The farther the raisin is from you, the faster it's moving from you. Well, actually, then, we can go ahead and take this expansion, the universe is expanding, and I think one of the videos, maybe even two of the videos we watched, said if it's expanding now, what was it doing if we go back in time? So basically, if you go back in time, reverse expansion, you get contraction. Your contraction to what? And actually, we're kind of building up to contraction to an object we call singularity, which was all of the matter, all of the energy that our universe ever would be into one object. And then it unfolded, and we'll talk more about this next week, in an event we call the Big Bang. So again, the term cosmology means kind of the way our universe is set up. A cosmological principle means kind of with regard to our universe, some basic understanding. So it looks like our basic understanding is what are we expanding into? Nothing. Okay, there is no edge. Okay. So I think one of the videos we watched said this idea of the expanding universe can be thought of as kind of as if you blow up or inflate a balloon. And kind of on the outside of the balloon, those A, B, C, and D, those actually black dots could be our galaxies. So as the balloon inflates, okay, again, what's it expanding into? Nothing, okay? But this is where I say it really does have an edge. But the balloon expands, okay, and each one of those dots get farther from each other, kind of like our expanding universe. So this little diagram right here, again, is what I drew just a minute ago. This is Hubble's law. Each one of these dots are galaxies. Okay, so along the x-axis we have how far away is that galaxy from us, and along the y-axis we have how fast is it moving. Okay. And the way it works, and you can kind of convince yourself if you want to, and I've done this before, but you can take the slope of that line. The slope of that line is what we call h naught, or Hubble's constant, the slope of that line. And if you take what we call the inverse of the slope of that line, or 1 over h naught, okay, actually what you are doing is basically going back to a point where, I think this would be right, going back to a point where the recessional velocity was 0, okay, everything was all together, okay, how long ago did that event occur? And from this curve you get to age our universe at about 14 billion years old. Okay, and again, we're going to talk about the Big Bang more next week. That's a light subject, right? Okay. How old is their universe? 14 billion years, according to Hubble's law, Hubble flow. So this is kind of an aside thing, a little bit. So if we have an expanding universe, we kind of have a hard thing to combat when we want to say an object is here. Because one of the problems we're fighting is that it takes light from objects a certain amount of time to get to us. So for instance, if we're looking at an object that is 4 million light years away, okay, looking at an object that is 4 million light years away. So we're down here. Let's see, where are we? This is us. Whoops. The one on the left is us. Okay, and this is our object of interest. Okay. So 4 million, the object's 4 million light years away. So let's go 4 million years ago. 4 million years ago, this is where we were. 4 million years ago. The universe is expanding. Where did that put us? Well, that put us up here, and that put our galaxy of interest over there. So we finally get out our telescope, and we're going to look at that object, that it takes light from that object 400 million years for that light to get to us. Okay, so we have to let 400 million years elapse. Okay, now that object, like I said, is up there, we're here. But what we're seeing actually is light that was sent, it's confusing, light that was sent by that object as it was here, and we caught it here. Do you know what I'm saying? It's like, oh, I know. It's like if you play with your dog, okay, and you want your dog to catch a ball, right? And so actually you know, you and your dog have this understanding, kind of how this works. So you know that your dog is going to jump up, and you know he's going to catch your ball here. Well, it takes a little while for your ball to get there, and it takes a little while for the dog to get up to the ball. So you have to kind of gauge all of that. Okay? To me, that's kind of what we have going on here. So bottom line, I don't think it's a cop-out. It's a little bit of a cop-out, I think. So basically what astronomers do, I think, is not worry about it. Okay? There is a difference between the actual location of the galaxy, which is kind of shown over there, you know, the actual location of the galaxy, of course. of interest with the supernova event is really here now, okay? But look back is there. So we kind of just go with the look back, okay? And know it takes a while for that light to get to us, and know that that object is moving. Both of those things, okay? So we ran into this term before, and I think actually it might have been on your Unit 1 exam, okay? The idea that actually there is an edge to our universe that we can't see beyond. So if our universe is 14 billion with a B years old, 14 billion years old, does it make sense that I would be very surprised if we could see an object that was 15 billion light years away? Because if we saw an object that was 15 billion light years away, then actually the light that finally got to us had been in transit for 15 billion years. But if our universe is only 14 billion years old, okay, that doesn't work. See how that works? And to me, if you kind of take that, well, how far can you see? Well, we can see in light years, in distance, only the age of the universe, okay, which is 14 billion years old, 14 billion light years away. Yeah, that makes sense. So I have a little video to kind of show you this, but this one hurts my brain too. Okay, so way back when Hubble actually noticed that, and we talked about redshift before, that Hubble noticed that the galaxies, the farther the galaxy is from us, the faster it's moving, and then the faster the redshift it gives us. When something's moving away from us, it gives us a redshift. The faster it's moving, the greater the redshift. Well, there's this other redshift, and this other redshift actually is associated with the expansion of the fabric of space and time. I like this little image of the balloons again, the expanding balloons. Okay, so the balloon is our universe. Our universe is expanding. The balloon is expanding. And you can kind of see the crosshairs on that. The crosshairs would be like the fabric of space and time. So the fabric of space and time, we're not creating the fabric of space and time. Whatever space and time we had at the time of the Big Bang is what we have now. So it's expanding. So what this is showing you actually, as the fabric expands, so also I kind of think of it like this. If you have an energy that is traveling in or on the fabric of space and time, that energy also is lengthened or elongated. So one of the a key understanding of cosmology is that we have this thing called microwave background radiation that is part of the Big Bang, and we're going to talk about that next week. But basically, microwaves, what are microwaves? Really long microwaves, okay? Basically, what that is energies that have been stretched, okay, because of the stretching of the fabric of space and time. Okay, then that's called cosmological redshift. So I have a little video to show you. See what you think. So here are some photos of galaxies. So remember, and again, back to Unit 1, I think it was on your exam, I said something about taking baby pictures, like the farther away the galaxy is, the more it is, the longer it took for the photons to get to us. So basically, it's more of a baby picture. A close galaxy, we kind of get kind of that galaxy has lived longer, okay? Looking farther away, it took longer for it to get to us. So actually, what you're looking at here is, I'll put BB for Big Bang over there on the left. Okay, this is the Big Bang, and this is now, basically. Okay, so basically, these galaxies right here have had a long time to age. Okay, and then actually, as we go back further, okay, they are younger. When I say younger, I mean they're more recent to the Big Bang. Okay, so actually we can see that galaxies have kind of evolved as they grow. Now, to me, what's most dramatic is this right here. These would be the earliest, the most distant galaxies we see, the earliest galaxies after the Big Bang. And I think the word I like, it's called disturbed. I think we heard it on a video too. Okay, they're disturbed. Just their shape looks disturbed. Okay, I think that early after the Big Bang, well, one thing, early after the Big Bang, the universe was a lot smaller than it is now. So early after the Big Bang, the universe was a lot smaller, things were closer, a lot more galactic interactions. So these are very kind of disturbed babies. And then they kind of grow up and mature. And I think we watched a video where it was a woman who said that how they become more organized as they age, unless they run into another galaxy. So we use the word protogalactic clouds as basically a big old nebula, because we've talked about a nebula that can spawn the sun, a solar nebula. We've talked about molecular clouds that can give birth to a bunch of stars, a stellar nursery. Now we're talking about something even larger than that. Okay, a galactic cloud that can give birth to a galaxy of stars. Is that not amazing or what? And I think the video, one of the videos we watched mentions this new telescope that's not going to replace the Hubble Space Telescope, but the Hubble Space Telescope is aging and you can't fix everything. It's the James Webb Telescope, and it should help us understand kind of how galaxies age. So when we talk about kind of the evolution of a galaxy, or galaxies in general, galaxies in the past, galaxies now, actually, I don't think there's like new galaxies being formed. Okay, there are new stars being formed, but kind of the galaxies we have galaxies merging. Okay, but early on after the Big Bang, basically what it looks like was the space and time was uniform with regard to matter. Hydrogen and helium, pretty darn uniform. But it had to have a few kind of inconsistencies, kind of these little dense regions where galaxies could form. Okay, so let's see, I'm trying to decide protogalactic cloud. So this is kind of early on after the Big Bang, and we'll talk more about these little seeds, but can you kind of see tiny little seeds there, and they kind of get bigger, they get more distinct over time. That's actually going to give rise to a galaxy of stars there. One of the things that we know about kind of the stars that were born shortly after the Big Bang, and we'll talk more about this, is that they were really massive. And one of the things we know about massive stars is they live their lives quickly and die. So remember I said there are 3 types of galaxies. There are elliptical galaxies, spiral galaxies, and actually there's regular spirals and barred spirals, and then there are irregular galaxies. So scientists have thought kind of why you get different types of galaxies, the spiral versus the elliptical. And 2 options here. One is that maybe kind of the protogalactic cloud that formed that galaxy of stars was slightly different. And the other, and I have a slide coming up here in a minute, or you kind of get ellipticals and spirals as galaxies dance with each other, as they interact with each other. So starting with the first one, how could you have a different protogalactic cloud lead to a different type of galaxy? And so that's actually what's being shown here. This is the effect, focusing the effect of rotation. And the way you read this, by the way, this thing right here, that's your protogalactic cloud. I'll call proto-G for galactic cloud, kind of on the left there. So there's your protogalactic cloud. This one on the top here, I'll put E for elliptical galaxy. This one on the bottom, I'll put S for spiral galaxy. So basically, if it was rotating, I'll put rotating over here. If it was rotating, okay, then your protogalactic cloud, you could get a spiral galaxy. If it was not rotating, I'll put R for rotating, then you get an elliptical galaxy. That makes sense. And actually, there's one more kind of difference in the protogalactic cloud, and that would be density. So again, on the top, you have elliptical galaxies. On the bottom, you have a spiral galaxy, okay? Elliptical, E for elliptical, S for spiral. With regard to density, it's thought that if the protogalactic cloud was dense, okay, then you can go ahead and get an elliptical galaxy. If it was sparse or not dense, actually you have a fighting chance to get a spiral galaxy. So that's kind of with regard to those two types of galaxies, what they think the protogalactic cloud could lead to. The other thing is you can get different galaxies as they interact with each other. And I'm going to show you this video here about galaxies interacting. But this actually is a photograph of galaxies colliding. They are NGC objects, not Messier objects. I don't know if I've emphasized it much, but I love the Messier objects, but that's not the only catalog in the book. Okay, NGC objects. They're galaxies interacting. I see this and I kind of think of the Milky Way and Andromeda, and I kind of wonder what that's going to look like. So I use the word disturbed for those early galaxies. Okay, actually, like I said, they could interact with each other when the universe was smaller. Such a simpler universe. So down here at the bottom, one of the things that physicists, all scientists count on, not just physicists or astrophysicists, are these computer simulations. So that's kind of what you're seeing down here, the dance of galaxies, okay? One of the things, if galaxies do combine, we call that a merger, okay? So if the galaxies are similar in size, like the Andromeda and Milky Way, that would be a merger. If the galaxy, and I have a minute to kind of show you something that's called cannibalism, if you have a big galaxy gobbling up little ones, that's actually called cannibalism. Sometimes I think scientists had a fun time coming up with some of these terms. So let's take a look at the video. I think what the Andromeda and the Milky Way are going to do is called a merger, but this is an example of cannibalism. So actually, we said that elliptical galaxies can get humongous. So this is where an elliptical galaxy is gobbling up other galaxies. Galactic cannibalism. Another type of, or another consequence of interaction actually can create what they call a starburst galaxy. So starburst galaxies are where paragalaxies are dancing, and basically one kind of runs into the other, maybe a merger there. So let's leave this last topic about the black holes. We'll leave that for Monday because we've got time. And so the assignment for this chapter won't be due until Wednesday. Okay? Let's do it that way.